can't believe how good it's going to be.
Right. All right. So I didn't know how I was going to start this lecture, and the point of literally everything that I'm doing at this point in my lectures is to try to get a sense of our place in the universe, where we are, and it's really and the more that I do this as a way of preparing for the class, the more I'm getting smaller and smaller personally. I hope you all are as well, getting smaller and smaller, because I think that the only way, personally, that I think that I can deal with my very short spate of time on this earth is to see me in relation to the 13.8 billion years that the universe has existed, and the 90 billion light years of the observable universe that we live in. So to try to understand those two numbers is really the goal of everything I'm doing here. You know, so I tell you a little bit of this, and I tell you a little bit of that, and it's incomprehensible. So here's one, a little bit of incomprehensible that I thought I'd start with. So this is the Andromeda Galaxy. It used to be called the Andromeda Nebula. And at some point in the history of the world, before any of you were born, but in the beginning of the 19th century, the 20th century, we grow to know that this nebula was a galaxy, and this nebula wasn't in our own nebula, which was called the Milky Way galaxy or nebula, but that this nebula exists outside of our galaxy, and it is a galaxy very much like our own, but bigger. So the Milky Way, which we cannot see because we live within it, is like this, but a tad smaller. Let's say the Milky Way has 400 billion stars. I've seen a number recently up to 600, but that's meaningless. They keep changing the number from 100 billion to 400 billion, 600 billion is a nice number. Depends what you're counting. The number for this galaxy is a trillion. A trillion. It's 2.5 million light years away. Now you can't even, a light year is incomprehensible. A million is somewhat comprehensible, but a million light years is incomprehensible. And this has a trillion stars. Incomprehensible. These are, so I came up with just one more little thing that would help comprehend it. So, not that anything of this can be comprehended. So this is a photograph taken with a lot of telescope time and a lot of pictures put together of the same Andromeda Galaxy. This is the center. This is just that side of the galaxy. Okay, so you don't see. I'll put the other one back for a second so you can see that it's the same thing, although it's tilted in a different direction, I'm afraid, than this picture is. But the tilt is arbitrary. So there's the Andromeda Galaxy. There's, in this picture, 500 billion stars. The thing is that you can see them in this picture. What looks like sort of a nebulosity here is actually resolvable into stars. And because I have this as a picture, I can make the picture bigger. So now the picture is bigger, and you see the stars there. I make it even bigger, but what you're seeing here is that's a star, and that's a star, and that's a star, and that's a star. Those stars are in our galaxy. Anything that looks like it's a star is in our galaxy. Anything that looks like it's too small to be a star is in that galaxy. So this just looks like a pattern of dust, like a cloud. As I zoom in more, it still looks like a cloud. And now, maybe you're beginning to see that on the screen, there are lots of little dots. Those little dots, each of them are a star. Each of those dots on the screen are a star. Maybe 1 trillion is a hard number to understand.
But they're not in our galaxy.
They're not in our galaxy. They're in the Andromeda Galaxy, which is 2.5 million light years away from here. Each of those are stars.
What's the big stuff?
In our galaxy, 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 in our galaxy. Everything that looks like it's just a grain of sand is in that galaxy. There's 1 trillion stars in that galaxy.
And they have planets.
See?
And they have planets.
And every half of those stars have planets. 1 trillion stars, half of which have planets. The other half of which may be double stars. Half the stars in the sky are double stars. So to a large extent it's harder for them to make long-lived planets. They can make planets, but the planets go crashing into the star at some point. Or they form further out and they're not good for life, or they can't form close enough. So some of these could be candidates for life. They could literally, this entire galaxy could be filled with intelligent life. They could be literally communicating with each other through all sorts of who knows what mean. They could be traveling between each other because they're advanced, because the universe has been around for 13.8 billion years. This galaxy has been around for a comparable length of time, let's say 10 billion years. We've only been around for, say, 4.5 billion years. And it took us 4.5 billion years to build a civilization like our own so we could talk about this. Maybe this whole thing is filled with civilizations. We'll never know. We'll never know because it's too far away to discuss. If they are busy communicating with each other, chances are we won't know, ever. In fact, we won't even know if it's happening in our own galaxy. But we're looking because we can look at the things that are close by to see if there's anything going on that might border on intelligent life in the universe. And so if it's close by, there's a chance we might pick up the signal. But if they're talking to each other, we're never going to get that signal. Unless they have a laser and they're pointing it directly at us, Because if you point a laser directly at us, maybe we would pick it up. Who knows? But anyway, that's not my point.
We are looking for Earth-like similarities.
Right, but we can't determine anything at all. All we can do is learn from what's near us and then extrapolate wildly to say what's true there. So we have discovered planets nearby us, and to the extent that that's true and that we can develop a set of statistics about that, we can begin to say, well, that's probably true over there as well. But we have no evidence. It's just statistics. If you get enough information about anything statistically, if you get a large sample, you can begin to say things that are true about things that you don't see. For example, if you are a person who makes a product, let's say French fries, and you are concerned that the French fries might be contaminated by some sort of bacteria. Maybe that's a thing that you're concerned about on an ongoing basis. And you make 1 million French fries a day. If you sample 1,000 of them, or even 100, you can determine what's true about the other 199,000 French fries you didn't sample, because you took a big enough sample to draw a conclusion. The sample will tell you the answer, what's true of the things you didn't look at. So the sample of stars that are nearby us, we can then say, aha, if we have this true, then that's true where we can't see. And one of the things that's true is we haven't found anything like our Earth. But also we haven't looked hard enough. So we can't even give you a statistic on that. Okay. So the conversation in this class for the last, let's say, 10 weeks, 10 lectures, has been bordering on the idea of how do we know how far away these things are? How do we really know how far away these things are? It's not easy, and it's a game that has been played for centuries before the 20th century, but it was only in the 20th century that we began to actually solve the problem of how far things are away. So there's this little joke on the screen. Cepheid variables, or why Henrieta couldn't leave it alone. Henrieta Leavitt is the person who made it possible for us to discuss how far away everything in the universe is. Without her contribution, we would not know how far away everything is. So in the past, we tried to figure out how far away the sun was. A guy named Aristarchus, he said, well, look at the moon is over there, okay, and the sun is over there, and I can do the geometry, and I can compute the Earth-Sun distance if I can figure out this angle between the moon and the sun, and just all I have to do is stare at the sun carefully. But he didn't have any instruments worth a damn, any instruments. So he got this angle very wrong. He got the angle very wrong, and so the number he got for the Earth-Sun distance was very wrong. But it was a bigger number than anyone had ever thought. 97 times the distance between the Earth and the Moon. It's a much bigger number than that, 100 times bigger, or at least 100 times bigger than that. But it was the first time that we knew how far away things were. So then, if you know how far away things are, then if you know how far away the sun is, then the same piece of work can be said, well, the sun is a star, those things in the sky are also stars, which, by the way, is a big leap. It's not obvious, right? But some people made that leap. That's a star, our sun, those are stars as well. They're dimmer, so they must be further away. How far away are they from us? And if you do that sort of calculation, you come up with big numbers too. And so you really get to know that the universe is bigger than you thought. And that's terrific, even if the numbers are totally wrong, and they were totally wrong. One of the reasons they were totally wrong was the sun is not the same as those suns. Those stars are all different. We didn't know that at the time. It took another 10, 20 years to know that those stars are different from each other, and you can't depend upon them to be like our own star, so you can't judge distance by how bright they are. If you knew how bright they were intrinsically, you could then know how far away they were, but you don't know how bright they are intrinsically. What you need is a standard candle. Imagine this is a candle, and it's a standard candle that you can buy in the store, and if you light this candle and bring it any distance away from you, that candle gets dimmer and dimmer. And the dimmer it is, you can tell that it's further away. It's a standard candle, and it's the way that we could judge the distance to the stars in the universe if we only knew how bright this was. But we don't. But what Henrietta did is she looked in the sky. So this is the Milky Way. And if you are south of the equator, you can see these things in the sky with your naked eye. And those things are dwarf galaxies that orbit our own galaxy, the Milky Way, and have each of them hundreds of millions of stars inside of each of those. So what we know about this one, which is called the Small Magellanic Cloud, named after Magellan, whose crew discovered it, and the Large Magellanic Cloud. The Small Magellanic Cloud is clearly a set distance away. Wherever it is, however far away it is clearly all of the stars there are the same distance. So if you look in the sky and you see that that there's something going on there, you know whatever's going on is taking place at that distance. So if you look in the sky, why Henrietta couldn't leave it alone, what she saw in the sky was this. She saw that there were stars in the sky that were variable stars. That means that their brightness varies over time. And she knew from other work that she had done that the period of a particular star would repeat again and again. A star which is variable, some stars which are variable, repeat like clockwork. Brighter and dimmer and brighter and dimmer and brighter and dimmer within a time period of a few days or even a month. It gets brighter and dimmer. And other stars in that same cloud got brighter and dimmer faster. And other stars in that same cloud got brighter and dimmer slower. And the ones that were the brightest got brighter and dimmer slower. And the ones that were dimmest got brighter and dimmer faster. And so she was able to plot a graph of luminosity, brightness, versus period, days. And she said, even if she didn't know how far away the Small Magellanic Cloud was, she still was able to draw this graph. And this graph says, if I can determine the period of the variable star, I can then say what the luminosity is. All I need is just one data point. I just need to know one Cepheid variable star. I need to know just one Cepheid variable star. I need to know the distance to just one. I don't have to go to the Small Magellanic Cloud. I can look nearby in our own galaxy. Let me check what's in our own galaxy. Let me find Cepheid variables that are in our galaxy. And let me see if I can find the distance to any one of those. And you could, because you could triangulate, because the Earth moves in its orbit. And the Earth, even then, and still does, move in its orbit. And so all she had to do was find a Cepheid that she could actually get the distance to. And once she got the distance to that star, she knew what the luminosity was of that star because she knew the period of the star. She could then make this an absolute luminosity, and she was then able to say, aha, I can now calibrate Cepheid variables. I can now, anytime I find a Cepheid variable in the universe, I can now tell the distance to it. And now I have a video to play. And this video is, this video gives me goosebumps because it is like, if you will, there are a lot of scientific discoveries that happen in our world. And to say that any given one is bigger than any other one is really crazy. But on some level, the discovery you're about to see is not like Einstein, who came up with the theory of general relativity. It wasn't so much a discovery as a theory, and it was validated. This is a discovery. This is an event. It took place in a single night, perhaps, or in a single month. This is about a guy named Hubble. And you know, he has a telescope named after him, so he must have done something really important.
Visible to the naked eye and studied by Persian astronomers around 900 AD, the Andromeda Nebula was thought to be a part of the Milky Way. In fact, it was thought that all the stars in the universe were in our Milky Way galaxy. That changed in the early 1900s. In 1923, Edwin Hubble found a Cepheid variable in the nebula. The star altered the course of modern astronomy. The star goes by the name V1. Here's Edwin Hubble's image of Andromeda, which was made on a 4x5-inch glass plate and dated October 6, 1923. He originally identified 3 stars and marked each of them with an N for nova, a class of exploding star. Later, Hubble realized that the nova at the top right was actually a Cepheid variable. He crossed out the N and wrote var for variable. He added an exclamation point because he knew that this variable would allow him to calculate the distance.
So just look at the dates. December 17th, 2010, 2021, December 30th, this is January 26th. Look at the brightness of that star. It varies. You have to know what you're doing to know that this is the most important thing that has ever happened in astronomy, almost.
And this was,
Indeed, once the period was measured at 31.4 days, he knew he had another galaxy.
He knew he had another galaxy. Did somebody say something?
I said, is that credited to Henrietta?
It is credited to Henrietta. But no, the data, that graph you saw on the screen that I showed you is credited to Henrietta. He used that information to determine that Andromeda was 2.5 million light years away. Henrietta didn't get credit for that. They didn't name the telescope after Henrietta. They named it after Hubble. Okay, but certainly he couldn't have done the work without Henrietta having said variable stars can be used as a standard candle.
He knew he had another galaxy. Before V1, distances to stars were measured in thousands of light years. After V1, the universe became a much bigger place. V1 was over 2.5 million light years away.
Wow, it's amazing.
Andromeda is a beautiful, barred spiral galaxy with 2 spiral arms that glow with a massive number of new stars. This is very much like our Milky Way. But
So it is amazing. Does anybody feel like I do that this is literally a world-changing event?
Yes.
Yes.
You're in awe when you see that.
Yes.
Too.
Yes. I am in awe. So I'm in so much in awe that I can't speak, if you will, because what has to come in this lecture, if I can get to it at all, actually I probably won't get to it, is, okay, that's 2.5 million light years away. That's next door. That's around the corner. That's hardly any distance away at all, because the universe is bigger than that, and it's filled with all of those. Well, we wouldn't know it was filled with all of those and so far away if it wasn't for this. So now we know that that is a galaxy. So when we saw other things in the sky that looked like Andromeda, without even doing a measurement, we could go, oh, that's far away, not in our galaxy. That's far away, not in our galaxy. And the smaller you see, the smaller ones, not that they're standard candles, but the spiral galaxies that are smaller must be further away. The universe is very big. Suddenly, overnight, instantly, the universe became, from the size of the Milky Way, which is 100,000 light years across, to billions of light years. Went from 100,000 light years to billions of light years overnight. I mean, that's insane. There was never a moment. It's faster than the Big Bang. The universe got bigger.
What year was this?
2000, I think, we think the numbers we saw on the screen were 2010.
When Hubble made his
1920? I'm sorry. Yeah. Right. So, it isn't. So we're doing the cosmic distance ladder. So the Cepheid variables get us. The Cepheid variables are a star, and they're just a star. They're a big star, to be sure, but they're just a star. And the reason they change their brightness is they get bigger and smaller and bigger and smaller. Same mass, but they get wider for a while, and so they have more luminosity, and then they get smaller and they have less, and so they pulsate regularly. But they're only a star. So you can only see Cepheid variables for a small distance, because you saw that picture of Andromeda. There were all of those stars, and they were teeny itty bitty points of light. The Cepheid wasn't any brighter than any of those. It was maybe a little bit brighter than any of those, a teeny bit, because it's a bright big star. But certainly you couldn't see Cepheids across the universe. You want to know how big the universe is, and Cepheids aren't going to give you much help, but they will give you some help. Because while the universe, and I always think that that the universe has been organized for our benefit. Not that I believe in organizing anything, but I do think that the universe is well constructed so that we ourselves can learn about the universe. Imagine if the thing that I'm about to tell you next simply wasn't true. Then what I'm telling you next we wouldn't have a way, at least at that time, of knowing how far away those galaxies are there. Yes, they're further away, but how far away are they? Because there's lots of them, and we can't assume that they're a standard candle. The further it is, the dimmer, yes, but exactly, is it a big galaxy or is it a little galaxy, or the opposite? We can't tell. So is it a dim galaxy or a bright galaxy? We wouldn't know. We need something that we can use the Cepheid variables to calibrate the next measurement. So the universe has given us supernovas. Supernovas are the gift of, in more ways than one, to us from the universe. Supernovas, of course, have given us every heavy chemical element in our body, because the supernovas created all the chemical elements in our body except for hydrogen. Everything else was born inside a supernova. Thank you very much, supernova. But the supernovas have given us one more thing, and that is when they blow up, if they do it just right, they can become a standard candle. And the question is, how does something that blows up, how do we know how bright it is intrinsically. How do you know that, well, it was a big explosion or a small explosion? How do you know what the size is of the explosion? And because nature has decided to help us with the answer to this, nature has decreed a certain law of nature. And that law is that if you are a star and you are bigger than our sun by a teeny bit, our sun is 1 solar mass. If our sun was bigger than a solar mass, if it was 1.44 solar masses, 1.44 solar masses, you could do the physics for homework and realize that that star cannot survive forever, and eventually it will explode. That is like a law of the universe. Any star above 1.44 solar masses will explode. Okay? I'm not going to explain why. I'm not exactly sure why. I mean, I have read about it, but I don't think I can explain it sufficiently without changing the topic entirely. So I'm not. I'm going to simply say 1.44 solar masses. But wait a second. How do you get something that's 1.44 solar masses? It could be 1.43 solar masses. It could be 1.45 solar masses. How do you get 1.44 solar masses and be sure that it's 1.4 solar masses? And the way the universe is contrived to do this is by doing something like you might do in a recipe. You have a pot with a certain amount of salt, let's say, and you want the pot to have a certain salinity. So you don't know how much water is in the pot necessarily, so you add some salt, and then you taste it. It's not right. You add some more salt. Taste it. It tastes better. At some point, you add just the right amount of salt, and the pot contains just the right salinity, and by analogy, the star blows up. So how do you pour salt, or in this case, mass, into a star? How do you pour mass into a star? And do it slowly, so that at some point it reaches 1.44 solar masses. Well, in order to do that, what you need is another star, because stars are the ones that have all the mass. The universe is filled with mass, but it's just out there in a gas. It's not going to pour into the star and feed the star. Our sun isn't getting any bigger. It's been around for 4.5 billion years, and it isn't getting any bigger. And that's, so it's staying at 1.41 solar mass. But if our sun had a companion that lived nearby, let's say at the orbit of Jupiter, or even at the orbit of the Earth, and let's say that companion star was very different. Let's say that the star that we want to blow up is this one, and the star that we are going to feed it with mass is this one. It's a big one. And the big one is near the little one. And so the big one is dropping mass into the little one because gravity, because of tidal forces, because one can pull on one can raise a tide on the other, a tide high enough, big enough for the tide to come all the way into the little star that's destined to blow up. And so the little star that is destined to be 1.44 solar masses pulls mass from the big star. And at some point, that big star has given the little star just 1.44 solar masses. And then the little star will blow up. And when it blows up, it'll blow up exactly the same way as every other 1.44 solar mass star. It'll become a standard candle. It's called a type 1A supernova. There are lots of supernovas that are not type 1A. For example, if you'd have a big star, let's say it's 10 solar masses, it's going to blow up. It's not a type 1A supernova. It's a type 2, and it's useless for measuring distance. So type 1A supernova, yes.
If the sun is exactly the right size.
If the sun is exactly the right size,
Exactly the right size, and it gets a little bit bigger,
and it gets a little bit bigger,
it will explode.
it will explode.
Now,
Except for the fact that it can't get any bigger, so it won't explode. Except for that fact.
but wouldn't it get a little bit bigger because things are flying around, like
It-
comets and asteroids, and sometimes they must fall into
Well,
the
comets and asteroids can and do fall into the sun. Comets are known to fall into the sun all the time.
So at some point, wouldn't some tiny little thing put it over that?
Well, but the thing is, we know exactly how much, well, not exactly, but we know how much other stuff there is in the solar system besides the sun. And the biggest other stuff in the solar system besides the sun is called Jupiter. So if you threw Jupiter into the sun, which is unlikely because it's hard to give it a shove to get it there, but if you threw Jupiter into the sun would still be one solar mass. It would be 1.01 solar masses. So you need to do a lot of throwing of stuff into the sun to get it up to 1.44. Comets don't count. They're just specks of dust. They're your house isn't any heavier because some dust settled from the outside on your floor. You just have to clean it, but your house is still the same weight that it was yesterday. And comets are just specks of dust. So the sun isn't getting any bigger. There's hydrogen in outer space. This hydrogen is falling into the sun all the time. It is not enough of it. The space is empty. So the hydrogen from the space isn't falling in. Nothing can fall in. The only thing that can fall in is matter from a nearby sun. I said that most stars in the sky are binary. So it's one of those binary stars, close proximity to one to the other. One evolves faster than the other because they're different sizes. The little one has evolved into a white dwarf. This is what actually blows up. What actually does blow up is a normal star gets bigger. A normal star starts out like our sun. Our sun will get bigger over time. And in 5 billion years, it'll become a red giant, a supergiant. And then after that, he will shed its outer layers, and it will then become a white dwarf, the size of the planet Earth, which will still be about the mass of the sun, but the size of the planet Earth. So that's the star that's going to blow up. It's a white dwarf that's going to blow up. And its companion is another star, which has also gone through its red giant phase and is now becoming puffier and bigger. And it's become so big that its atmosphere is starting to intrude upon the atmosphere of the white dwarf stellar companion. And it's that gas that falls into the white dwarf, and it's that gas that adds to the salinity of that white dwarf, the mass of that white dwarf, to eventually give it the right mass in order for it to explode. The universe is very kind. I think it's very generous to have created this scenario for us, because without this scenario, we wouldn't know how bright supernovas are. It's hard. So, and how do you know it's a type 1 supernova? I mean, really, type 1A. Okay. I mean, that's there's some science in there. So this is a picture of that sort of thing that I was talking about, right? So there's the white dwarf, there's the red giant. In this case, it's a blue giant, and the blue giant is the atmosphere is being pulled tidally towards the white dwarf. It goes into orbit around the white dwarf, and then these gases eventually fall into the white dwarf, and the white dwarf gets bigger, heavier, more massive, until it eventually explodes. Yes.
Is the white dwarf bigger than the blue giant?
The white dwarf could be literally more massive than because they both were born at the same time,
Right.
exactly the same week they were born. Okay, and now this guy became a white dwarf, and this guy isn't a white dwarf. White dwarf is a late stage of stellar evolution. So this guy has gone through its stages of stellar evolution quicker. That means it's bigger. Because the bigger you are, the faster you evolve and eventually die.
So it has more mass, and that's why it's pulling.
No, it's not. No, it's not. The more mass isn't why it's pulling. It's just that it's the candidate that will. This was smaller. Now it became bigger, and as it became bigger, the envelope became bigger, and now this envelope can be pulled because there's less gravity holding this atmosphere in because it's far away from the central star. So this atmosphere of this star can be pulled towards this star because there's not enough gravity to hold it here. The gravity of this can pull it that way, tidally.
Isn't gravity based on mass
And distance.
and distance?
So
Yeah, but they're both the same distance from each other.
no, but the distance of this piece of atmosphere
Oh.
from the central is less, and so the gravity of this star becomes integral to where it decides to spend the rest of its life, and it can be pulled tidally in that direction. So it sucks it up. That becomes supernova. This star remains. So usually when you see a type 1A supernova, you can find the remaining star, because it requires two stars in order to make it up. Usually you don't see these things blow up beforehand. You don't see these things beforehand. You don't know where they are. There's a gazillion stars in the universe. You don't know what's going to blow up. You didn't look carefully. You have to spend money to look at a star and say, I'll use the big telescope on it. So nobody uses the big telescope on that, and nobody knew what was going on here, and then it blows up. Then you train the telescope on it. You look at it, you see the remaining star. But this one, you never saw. Yes.
The star that's the white dwarf, as it's pulling in with the gravity from that other star, and when this does explode, doesn't that destroy the remnant of the old star? Of the,
Does it not destroy the?
yeah.
The no. I mean, it certainly does a lot of damage. Okay, so it can literally wipe out the outer layers of the star. Whether or not the star is completely disrupted, it is questionable, and I think the answer is no. Although I think the answer may be maybe in some cases. You know, I mean, it certainly would be amazing. The star can blow up the other star. That would be cool. But I don't know. Yes.
Can the sun get smaller?
Yes.
And
Sun can get
still
smaller.
be stable? I'll use the word stable.
Yes.
Be the same, okay, and wouldn't it be getting smaller all the time now?
Our sun, yes, is getting smaller. Yes.
It is.
It is. Yes.
Yes, it's throwing off all
It's throwing off all this stuff, so it is getting
So
smaller.
is there a certain percentage or number that it can go down and still be fine?
Good question. The sun will always be a sun. Always be a sun. It will change its brightness over time, but it will lose mass over time. The amount of mass it's losing is small. So I would say probably less than 1% over its lifetime. So, but if I was wrong and and the answer turns out to be 10%, that wouldn't change anything that I'm saying. Even if it lost 50%, which is completely unlikely from my knowledge, it still wouldn't change anything that I'm saying. Because stars range from a size that is 20 times larger than the mass of Jupiter. They're called brown dwarfs, all the way up to red dwarfs, all the way up to yellow dwarfs, like our sun. So stars range in all sizes, but all not shapes. They're all round, and a star can be much smaller than our sun and still be a star. It will. Now, if you ask, can it do the services that we need it to do as a civilization on Earth? The answer is, long before our sun does anything interesting like get smaller, it's going to get a lot bigger. And the sun is going to get so big that, not massive, mind you, but size-wise, radius-wise, that it will absorb Mercury inside of it. It will then absorb Venus inside of it, and there's a 50-50 chance it could absorb the Earth inside of it as it grows larger. So there's no chance that we will survive any of the phases that occur afterwards, which is the white dwarf phase of the sun. So at best, we will see the red giant phase of the sun.
When you describe these things like explosions or absorbing mercury, are these explosions like we know them on Earth, are they instantaneous within a matter of minutes, or are they slow, universal?
No, they are minutes.
Just like boom.
They are minutes. I mean, literally, there have been explosions. When a star explodes, the insides come out, but it takes a while for the star to literally throw off its outer layers in order to do that. But the very center of the sun has something called neutrinos. And neutrinos are being made in the center of every star all the time, including our star. And we can look at our sun and see the neutrinos, the neutrino flux it's called, the neutrino flux coming from our sun. And when you look over there at that star, it's far away and you don't see it, so you don't see a neutrino flux coming. But if that star explodes, there will be a massive neutrino flux coming from it. And we have seen the neutrino flux come from a star a few seconds before the star explodes. Of course, we didn't know that until afterwards. But it's, I wouldn't say seconds, but certainly minutes, for it to explode. And this is... This, by the way, is a picture of a star exploding. Here, there you go. 0 times 0.85 seconds. 1.1 seconds. 1.2 seconds. So yeah, seconds. That's insane, right? That's insane. That is completely insane. I'm glad I found that. How do you know it's a type 1 supernova? Because this is a graph of luminosity or brightness versus time. Time is measured in hours or days. I don't know, this picture is not calibrated in either hours or days or months. So I really don't know the answer, but I'm going to say this is within hours or days of the supernova. So the thing is, supernova explodes, and you need to know something about this immediately. So there is a place on Earth where any astronomer or amateur astronomer, for that matter, can send a note saying, I see something, everybody pay attention. And all the astronomers on Earth get the note. And if somebody says, I see a supernova, everybody's getting into their cars, driving to the observatory or doing it remotely, and pointing their telescope at the supernova. Why do they do that? Because they want to record this graph. Because this graph will tell them whether or not it's a type 1a supernova or not. What happens here, in the center of the star, elements heavier than helium and carbon and oxygen are produced. those elements, as we've seen now, are thrown out in seconds from the center of the star. They're thrown out in seconds. And those elements that are created have a lifetime that is measured in minutes or maybe hours. And then those elements decay. And while they're decaying, they're creating the luminosity in the first place. So nickel creates the peak luminosity at I don't know what time. And then it decays, and then cobalt takes over to create the rest of the luminosity as it decays. So you need to get this graph in order to say, hey, it's a type 1a supernova. Because that's what type 1a supernovas do all the time. That's their signature. Yes. Isn't that beautiful? Isn't it beautiful? It's amazing. It's just amazing. Yes.
This may be a silly question.
You don't ask silly questions.
Well, this may be. You said it happens within seconds.
Seconds.
So wouldn't a computer be programmed to capture this information instead of some guy getting into his car and driving over there? It's too late.
Well,
to grab.
So I don't think they're driving to the car. I think most telescopes these days can be operated from any place in the world. So as an observer, you get time on a telescope. You don't necessarily, I think, have to go to the observatory to observe. I think, though, you do for other reasons, like looking up in the sky to see if it's cloudy. So generally there's somebody at the telescope anyway, no matter what.
But they may be pointing a different way.
They certainly are pointing it because the universe is very, very big, and in this case, I do not mean far out. I just mean there's. If anybody has ever heard this phrase, and I love it, and I'm sure nobody's ever heard this, there's 4 pi steradians of arc in the sky. If you look at a circle, a globe, and you want to describe what the angle that is subtended by anything that you are looking at, that piece of sky is called a piece of a steradian, S-T-A-R, radian. You may have heard the word radians when you were in school and you heard about degrees. Steradians are patches of sky. The bigger it is, the more steradians. This room, from here to here, all the way, is 2 pi steradians. The hole below my feet is 4 pi steradians. The telescope is pointing at 0.0001 steradians. It's not pointed in the right place. So it's not pointed, there are some telescopes that are literally designed to suck up more steradians in its field of view than any other, so it could spot this thing and not have to rely on some amateur astronomer that happens to be looking in that direction. There are literally telescopes devoted to looking at the whole sky. And so they can capture it, but then they have to tell the big telescopes to look at it. So it's all a game that is being played between various astronomers and various telescopes.
Did they ever determine how often the supernova occurs?
It only occurs
In
once.
time.
It occurs once. Oh, okay.
How often?
How often does the supernova? Well, obviously supernova only occurs once for that supernova.
Okay. Yeah.
The number of supernovas that occur in our Milky Way galaxy is supposedly either one every 100 years or one every 400 years. So there was one in 1004 that it lit up the sky for a month. So that was seen by everyone on Earth. And there was another one that was seen around 1600. But we haven't seen any in our galaxy since the invention of the telescope. And that's insane. None. All right? It's pretty amazing. So this is one of the best stories, as far as I'm concerned, I could ever tell in this class. This is, and I will tell you, I'll expand on this story next time. But the universe is genius. If I believed in God, I would believe that this was designed for us. Not just the universe designed for us, but all these phenomena designed for us that we could know the universe. because we know so much about the universe. It's amazing that we could even know anything about anything, and we know all these things now in our world. And let me say that the thing that I may fear most about dying is not knowing any more than this, because there's so much more to be learned. So anyway, we'll see you next week. Okay. Oh, and the attendance sheet as usual, so you can't leave. As I said, if this is stock market crash, don't bother coming. Or maybe you should come, so we can all commiserate. Yeah, come. So this is what we didn't talk about, by the way. That's next time.